Welcome to today's session. The overall goal of this session is there's some questions that came up around securing networks and how, for example, different subnets interact as ways to partition your network as part of an overall security solution, and the interactions of, for example, frequency and Wi-Fi, et cetera. So that's kind of the purpose of the topic today. So we're building up to, how to secure your network or techniques that you can use to help secure your network. But I've decided to kind of go through a lot of fundamentals up front to sort of create, the and level set people's knowledge. So there might be some things that are really obvious to some people, but I figure it's best to make sure everyone has a basic understanding of the underlying principles, so that the further, more complicated stuff will make sense.
And networks, and in the next video. And let's just jump right into it by defining our first term, host. Hosts are any device which sends or receives traffic. For example, your computer is a host, your laptop, your phone, your printer, your servers, those are all considered hosts. But we're also in the cloud days, which means there's many cloud resources that can also be considered as host. Cloud servers, for example. Moreover, we're also in the Internet of Things days, which means anything you have at your house that sends or receives traffic is also considered a host. That smart TV you stream to, those speakers that are all synchronized with each other, smart watches, your thermometer that you can control remotely, that refrigerator that reminds you when you're out of milk, all of those devices are sending and receiving traffic, and therefore can be considered as hosts. Why this is important is because all of these devices follow the same rules for how they communicate to the internet. Later in this module, we'll be looking at everything a host does when sending or receiving data from the internet. In doing so, we'll actually be explaining how all of these devices communicate with the internet. Hosts typically fall in one of two categories, clients or servers. Clients are the hosts that are initiating the request, and servers are the hosts that are responding to requests. For example, let's just say this is the web server for the website www.site.com. Well, when this computer over here is making a request to ask for the website site.com, it's initiating a request, and therefore it is considered the client. When the web server site.com is providing the content for site.com, it's responding to the request, therefore it is considered the server. Keep in mind, however, the terms client and server are relative to a specific communication. Meaning, at some point, this web server is going to have to update its files from a file server or a database server. Well, for that, the web server has to make a request to the file server to ask for new files. In that communication, the web server is the client and the file server is the server. We can take it a step further. This file server at some point might need to run some sort of software update. Well, when it's making the request to the update server to download the new software, it's acting as the client. And when the update server is providing the updates back to the file server, it's acting as the server. So the terms client and server are specific to the communication that is occurring. Now we've been calling this a web server, but I want to clearly define what that is. A server is nothing more than a computer with software installed which knows how to respond to specific requests. This guy right here is really just a computer that has software installed that knows how to serve web pages. You can turn any device into a web server by simply installing the proper web server software. It's the same way with the file server and the update server we discussed a second ago. In the end, they are merely computers with software that knows how to provide files or provide updates. Each server you encounter is simply a computer responding to requests. So that wraps up our discussion on hosts. Next, we want to define IP addresses. IP addresses are the identity of each host, and every single host must have an IP address if it means to communicate on the internet. Just like you need a phone number in order to send or receive phone calls, or you need a mailing address in order to send and receive mail, you need an IP address in order to send or receive packets on a network. This is what the IP address is. It is the identity of every single host. Now, these IP addresses are actually going to be stamped on everything that each host sends. For example, when this client over here makes a web request to site.com, on this packet, which includes what web page it is asking for, the client is going to stamp the source and destination IP addresses. The source IP address is going to be the client's IP address, and the destination IP address is going to be the server's IP address. In the same way, when the server responds by providing the web page, it's also going to stamp the source and destination IP addresses for that communication. Here, the source IP address will be the server, and then the destination IP address will be the client. Everything sent on the internet is going to have this source and destination IP address. Now, an IP address itself is really just 32 bits. A bit is a 1 or a 0, which means every single IP address is really just a different combination of 32 ones and zeros. What we do is we take those 32 bits and break them up into 4 chunks, which we call octets, and we convert each of those octets into a decimal number. This is how we get to what we know of as an IP address. The smallest binary number you can get with 8 bits is 0, and the largest binary number you can get with 8 bits is 255. That's why every IP address you come across is going to be 4 instances of the numbers 0 through 255. Now in this module, we're not going to be exploring binary. We've already created some videos that discuss binary. If you're interested in learning about binary and how this conversion happens, please check out those videos. There'll be a link in the description. Either way, that is what an IP address is. Now, these IP addresses are typically assigned in some sort of hierarchy, so let me explain that. Imagine this is the Acme Corporation, and the Acme Corporation owns every IP address that starts with 10 dot anything. Well, maybe the Acme Corporation has 3 different offices, one in New York, one in London, and one in Tokyo. And each of those offices is going to have a subset of the Acme Corporation IP space. New York might have everything that starts with 10.20, London might have everything that starts with 10.30, and Tokyo might have everything that starts with 10.40. Moreover, the New York office might have a few different teams. For instance, they might have a sales team, an engineering team, and a marketing team. And each of those teams would have their own dedicated IP address space. The sales team could have everything that starts with 10.20.55. The engineering team would have everything that starts with 10.20.66, and marketing would have 10.20.77. The London and Tokyo offices probably have those same teams as well, but each of their IP address space is going to start with the prefix for that particular location. This allows the IP address to sort of pinpoint where a particular host exists. For example, if we had the IP address 10.30.55.127, that IP address is the identity of a host that sits in the Acme Corporation, in the London office, on the sales team. Now, this breaking up of IP addresses into their different hierarchies is done through a process known as subnetting. In this module, we're not going to be covering subnetting, but we've already created some videos discussing how subnetting works. If you're interested in learning subnetting, please check out those videos. There will be a link in the description. For us, we're going to continue with our exploration of network devices. All of the hosts that sit inside each of these teams at each of these offices exist in what is known as a network. A network is what actually does the transportation of traffic between hosts. In its simplest form, anytime you connect 2 hosts, you have a network. If you plug these hosts directly into each other, you have a network. Before networks, in order to move data from this computer to this computer, you would literally have to walk up to this computer, plug in a disk, download some files, then walk over to the other computer, plug in that same disk, and upload those files. Networking and networks are what automated that process. They allowed these computers to share data with each other automatically. Now, if we take a step back, a network is really just a logical grouping of hosts which require similar connectivity. So let me explain that. At your house, you probably have some sort of home Wi-Fi network. On that network, you've got your computer, your printer, laptops, phones, a bunch of different devices which all have similar connectivity profiles, meaning they just use the internet or check email or something along those lines. Well, down the street from you, there might be a coffee shop that provides Wi-Fi for its tenants. And that coffee shop is going to have various customers that have various mobile devices that are all connecting to the internet. Well, these devices all have similar connectivity profiles. They just need access to the internet. But since they're coming from a different location as these devices, they are grouped into 2 separate networks. Now, networks can also contain other networks. For example, you probably have a school not too far from where you live, and that school has its own network. But within that school are a bunch of classrooms, and it's very possible that inside each of those classrooms, all the hosts in each classroom are grouped up into their own network. Now, these networks within other networks are sometimes referred to as subnetworks or subnets, and this is a very common occurrence on the internet. In fact, that illustration we just did with the Acme Corporation, with the 3 offices and the 3 different teams in each of these offices, well, the office location is a subnet of the Acme Corporation IP space. And the specific teams are a subnet of the New York IP space. So you can have networks within networks within networks. Either way, all of these networks then connect to each other. For example, you might be sitting at your house and might want to do some sort of working from home and be able to access the office networks. Or possibly you're studying from a coffee shop and you might want to access school resources. Well, instead of having each of these networks connect directly to each other in every possible combination, instead, all of those networks are connected to a central resource, namely the internet. In fact, what we know of as the internet is simply a bunch of interconnected networks. That's all the internet is. It's just a bunch of company networks connected to a bunch of school networks connected to a bunch of customer networks. Of course, what handles those connections are often the internet service providers, or the ISPs, but that goes a little bit deeper than we want to get at this point. Either way, that wraps up our discussion on hosts, IP addresses, and networks. In part 2, we'll continue our discussion by unpacking repeaters, hubs, bridges, switches, and routers. The key takeaway from this lesson is understanding what hosts are, understanding the designations client and server, understanding what IP addresses are and their hierarchical nature, and understanding what a network is, specifically that it is a logical grouping of related hosts which require similar connectivity. I hope you enjoyed this lesson. I want to thank you for watching, and we'll see you in the next one. Hello, welcome to the second part of our lesson.
So just briefly, I just want to point out, you don't really see it much, but when he talked about IP addresses, those are actually referred to as IPv4 addresses, and those are the ones that you typically see in your home, etc. But there's actually a new version of the internet that was created many, many years ago, but it still hasn't proliferated, I would say, into like regular people's day-to-day life. And the reason for that is because, as it turns out, the 32 bits of internet can only reference 4 billion unique addresses. Now, as you can probably guess, there are way more than 4 billion devices on the internet right now. And it's growing and growing. So what IPv6 did was, among other things, created a new 128-bit address space. So just something to think about, that there is, when you say IP addresses, that people refer to IPv4 addresses. And who knows, maybe in our lifetime, we'll actually see IPv6 addresses in the home. Anyway, did anyone have any questions about that first video before I move to the next one? Pretty basic stuff, but good. All right, here we go.
On network devices. This is discussed the concepts of a host, an IP address, and a network. If you haven't watched that video, go ahead and pause this video right now and watch the first video. There'll be a link in the description. In this video, we're simply going to continue right where we left off. Now, the main idea we want to teach in this video are these last 2 devices, switches and routers. But we can't really understand those until we understand where we've come from, so we have to start there. In the last video, we unpacked the idea of a network. We identified that a network is created anytime you connect 2 computers to each other using a wire. One thing to understand about sending data across a wire is that it decays as it travels greater and greater distances. If the 2 computers you're connecting are in the same room, then you don't really have to worry about it. The decay will still occur, but the signal will still get through, and therefore connectivity between these hosts is still attained. If, however, these hosts span greater distances, maybe you're connecting 2 computers on opposite sides of a building, or even in 2 different buildings, then you might have a problem. If the signal decays before it gets to the other side, then these 2 hosts cannot share data. In those cases, what you need is a repeater. A repeater is a device whose sole purpose is to regenerate signals. Anything that comes in on one end simply gets regenerated out the other side. This allows you to connect devices together which span greater distances. So far, we've been talking about networking from the perspective of connecting one host directly to another host. Well, if you add a third host, you now have to connect that host to all the other hosts which you've already established. And if you add a fourth host, you now have to connect this fourth host to all the hosts that already exist. And again, if you add a fifth host, you now have to connect this fifth host to every host that has already been connected. As you can see, connecting hosts directly to each other simply doesn't scale. Instead, we created devices which we could put at the center of every network and connect all the hosts to those devices. And these devices would then handle funneling communication between these different hosts. The benefit to these types of devices is that if a sixth host gets spun up, it's very easy to simply connect it once to that device, and now it has connectivity to every host that has already existed. That's what all of these are. And the first of these types of device that we're going to discuss is known as a hub. A hub is nothing more than a multi-port repeater. Earlier, we discussed repeaters, and we said all they do is regenerate signals. Well, hubs do the same thing, except they do it across multiple ports. For example, if these two hosts over here need to communicate, when one of them sends a packet to the other, it'll hit the hub, and the hub will simply duplicate that packet and send it out all remaining ports. That'll allow what this guy sends to arrive over here. This fixes the scale problem. A hub is the first device that allows us to connect multiple devices in the center, and now all of them have connectivity to each other. But as you can probably see, the problem with a hub is that everybody receives everybody else's data. These two hosts over here, which are uninvolved in the communication between these two hosts, are receiving a copy of everything they send. Which brings us to bridges. Here, we have two sets of hosts, all interconnected using a hub. And a bridge is meant to sit in between hub-connected hosts. Bridges, by definition, only have two ports. One port facing one set of hub-connected devices and another port facing the other set of hub-connected devices. Bridges will also then learn which hosts are on which side of the bridge. This will allow the bridge to contain communication to only the side that is necessary. For example, if these hosts again need to speak to each other, when they send data to each other through that hub, the hub is of course going to simply regenerate that signal out all ports. And notice that the bridge is going to be getting a copy of that packet. But the bridge knows that the other green host is on this side of the bridge, and therefore the bridge isn't going to bring that packet to the other side. The bridge is the first type of device that helps contain packets only to their relative networks. On the other side, if these hosts need to speak to each other, they can also send packets to each other through their hub, and once again, the bridge will not let those packets bleed into the other side because it knows the yellow devices exist on the right hub. And of course, if this device needs to send something to this device, the bridge is going to know that that traffic is going to have to cross the bridge, and the bridge will allow that packet to traverse to the other side. The main takeaway is understanding that bridges can learn which hosts are connected on either side of the two ports of the bridge. Now this finally brings us to switches. Switches are sort of like a combination of hubs and bridges. They are like hubs in the sense that many devices can connect to the switch, and they are like bridges in the sense that they can learn which hosts are connected to each port. The main difference is that they're doing it on a per port basis, which means if these two hosts want to speak to each other, the switch will know that the only ports that need to receive this traffic are the two that are connected to those green hosts, and will keep that communication contained to just those ports. Moreover, if these two hosts want to speak to each other, the switch will again make sure that that communication only flows between the relative ports. So this is how a switch is like a combination of a hub and a bridge. The formal definition of a switch that we want to use is that a switch is a device which facilitates communication within a network. Earlier, we defined a network as a logical grouping of hosts which require similar connectivity. Which means all of these devices over here all belong to the same network. Moreover, networks all share the same IP address space, which means this network owns all the IP addresses which start with 192.168.1.anything. And this host's identity is the IP address 192.168.1.33. And this host would be 192.168.1.66. And this set of devices could very easily represent all the different hosts on your home Wi-Fi network. Maybe this device is your printer, and this device is your laptop, and this device is your mobile phone, and so on. Or maybe this network and these devices represent all the PCs that might exist within a particular classroom of the school network. Or maybe, even further, all of these devices represent hosts that exist in the sales team of the London office of the Acme Corporation. One way or another, since all these devices are connected with a switch, they all belong to the same network. Now, let's go back to that example of the school network. We said that the school likely has many different classrooms, and each of those classrooms belong to their own network, which means this would be a more accurate representation of the school network. We would have classroom 2 owning that IP space and classroom 3 owning that IP space. Now, the reason you might want to separate these two sets of devices into their own network is because they might have different connectivity requirements. For example, maybe these computers over here all belong to the biology classroom, and all they need is simple internet connectivity. But maybe these computers over here belong to the computer science classroom, and they not only need internet connectivity, but also access to various cloud resources to do their studies. Well, since these computers have different connectivity requirements than these computers, it's a good idea to separate those out into separate networks. Now, in both cases, we can still use switches to facilitate all the communication within the networks, meaning this switch can handle all the communication between these three hosts, and this switch can handle all the communication between these three hosts. But what happens if this host down here wants to speak to this host on a different network? Well, if a switch can only facilitate communication within a network, we would need another type of device to handle the communication between networks. And that device would be a router. A router is a device whose primary purpose is to facilitate communication between networks. At the very least, you're going to need that router to connect you with the ultimate network of networks known as the Internet. So let's unpack this further. Routers provide traffic control points between networks. Let's say we wanted to limit the traffic that could go from this PC to this PC. Well, since these two PCs are on separate networks, all that traffic has to flow through the router, creating a great place to add security policies or traffic filtering or even redirecting that traffic elsewhere entirely. Since routers sit on the boundary between networks, they provide a logical location to apply security policies. This type of security filtering isn't traditionally available on switches. These days, there are modern switches that can do such filtering, but it is generally accepted that the devices sitting on the same network don't typically need filtering for traffic traveling within the network. If you had devices that needed different types of connectivity, you'd want to place them in different networks. The network boundary is what it's meant to be, the logical separation of devices. The way routers work is that they learn which networks that they are attached to, meaning this router is going to learn that on this interface it's connected to the 172.16.20 network, and on this interface it's connected to the 172.16.30 network, and out here is the direction to go to the internet. The knowledge of each of these different networks is known as a route, and all these routes are stored in what the router calls a routing table. A routing table is therefore all the networks that a router knows about, and the router is going to use this routing table in order to funnel traffic out the appropriate interface. Now, when we say a router learns which networks they are attached to, what we mean is that a router has an IP address in every network that they are attached to. For example, when this router is attached to this network, it is given an IP address in that network. This interface's identity is the IP address 172.16.20.1, and this interface's identity is the IP address 172.16.30.254. This IP address is going to serve as what's known as a gateway. A gateway is a host's way out of their local network. For example, this host over here has the IP address 172.16.20.33. But if that host wants to speak to something on a different network, it knows it's going to have to go through a router. And the IP address of that router is stored as that host's default gateway. Notice this host has a default gateway of 172.16.20.1. That's this interface IP address of that router. Now, if we go a step higher than that, routers are actually what create the hierarchy in networks and IP addresses that we discussed in the prior sections of this lesson. For example, the New York office of the Acme Corporation that had all the different teams that each had their own IP networks, well, each of those networks are connected to different routers. and each of those routers are then connected to another router. And if a host in the sales team wants to speak to a host on the marketing team, it's going to use its gateway, which is its closest router IP address, which is then going to send the packet to the next router, and then finally to the host on the marketing team. The Tokyo office of the Acme Corporation is likely going to have a similar setup. And both of these routers are then likely going to connect to the internet. The internet is nothing more than a bunch of different routers itself. Meaning, if a host on the marketing team wants to speak to a host on the engineering team in Tokyo, that host will send the data to the router, which will send the data to the next router, which will send it through all the routers on the internet, which will finally send it to the Tokyo router, and finally to the engineering team. And that is how data is going to flow across the internet. And that is the role that routers play in making that possible. Now, the last idea I want to leave you with actually involves pulling back the definition of switches as well. There's something important you have to understand about what we've defined as routers and switches. Routing is the process of moving data between networks. A router, as we have described it, is simply a device whose primary purpose is to perform routing. In the same way, switching is the process of moving data within networks. And a switch, as we have described it, is a device whose primary purpose is switching. The reason I bring that up is there are many other types of network devices that exist out there. Access points, firewalls, load balancers, layer 3 switches, proxies, and there's even devices that only exist in the cloud, like virtual switches and virtual routers. One way or another, all of these devices are going to perform routing or switching or both. So later on in this module, when we describe what a router does or what a switch does, what we are actually describing is what any device does that implements routing or any device does that implements switching. And with that, we close our lesson on network devices.
Hopefully that was all, again, fairly straightforward. There was a few comments. Larry has a question.
How is an IP address established and who does it? Excuse me.
So there are two ways you can establish an IP address. One, you can go into the configuration of your computer and you can set it. Okay. More commonly nowadays, there's a protocol called DHCP, the Dynamic Host Control or Configuration Protocol. So when you connect your device to your ISP, your computer will ask for an IP address, and the ISP will give you an IP address in the network. Okay. If you do it manually, you could set an IP address that's not in the network, and then your traffic won't flow. Like the router will just throw out or the switch will throw out your traffic, and it just won't work. So DHCP is the standard way. And in your home router, you probably have a DHCP server running. Yeah.
How do they ensure that there's two people don't get the same IP address?
They cannot. So
How?
if, for example, if everyone is using DHCP, it's up to the DHCP server to keep track of that. And they use this concept of leases. So when you get an IP address from a DHCP server, it gives that to you for a certain amount of time, the time of the lease. And the owner of the network specifies that. So it could be 1 hour, it could be 1 day, it could be 1 week. Okay. And the DHCP server knows to not give out the same IP address as long as someone theoretically has a lease for it. Now, that doesn't mean that the computer that has the lease doesn't keep it beyond the lease. And if that happens, then bad things can happen. And you will see that. Or if you manually set an IP address to one that someone else is already using, bad things happen. Now, when you have intelligent switches, they can detect that stuff, and then they'll shut the port down for one of them to avoid, craziness. But yeah, as long as everyone uses DHCP and they follow the rules, the right things should happen. But yeah, it definitely can happen. That
Thank
makes
you.
sense? Sure.
Hey, Seth, I got to tell you something. It's really interesting.
Yeah.
I'm old enough to know, I'm 90, so I'm old enough to know I worked as engineering before computers came along.
Yeah.
And so what did they do at Hanscom? They say, Dave, you're going to be in charge of the computers guys because they needed a civilian to help, to manage it. Well, I didn't know my behind from the elbow. But anyway, getting to the point, they said they had this router over here, and they started talking. So I said, what the hell is a router? Then they started telling me. I said, oh, why don't you call it a programmable junction box?
Sure.
You see what I'm saying? So I learned from zero about all this stuff, and then I related to the phone company. If you ever been to the phone company and seen all those rows of switches, mechanical switches going up and down, I did as a young engineer. I saw this stuff. This is telephony digitized.
Yeah, exactly. And just so you know, all of this discussion is about the internet protocol, IP. But like the phone companies have their own switching networks. They don't use IP. They have different protocols that they use for routing traffic that has different characteristics than, that make more sense for the phone for routing voice traffic, for example.
David, can we hold the comments until the end, please? And the historical facts. Let's get on with the basics that Seth is presenting.
Oh, yeah, this is fascinating. Go ahead.
So does anyone else have any other questions? There was a few in the comments that I tried to answer. So I won't repeat them in case you're curious, and hopefully it will be a little more clear in this next video. Now, this next video is about what's called the OSI model. It's kind of like the academic way of describing the various layers of a network, in terms of, let's say, sophistication or complexity. It, I guess, would be a way to think of it, starting at the very physical layer and going all the way up to the application layer. And I think as part of this, some of the questions you may have will also make a little more sense. But I think understanding the OSI layer on top of these foundational things will be quite helpful for the last section on network security. So here we go.
To another lesson from the first module of my new course on network, simply a direct continuation of what occurred in lesson 1. That said, let's get into discussing the OSI model. The overall purpose of networking as an industry is to allow two hosts to share data with one another. Before networking, if I wanted to get data from this host to this host, I'd have to plug something into this host, walk it over to the other host, plug it into the other host. Networking allows us to automate all that by allowing the host to share data automatically across the wire. Now, for these hosts to do this, they must follow a set of rules. This is no different than any language. English has a set of rules that two English speakers must follow. Spanish has its own set of rules. French has its own set of rules. While networking also has its own set of rules. The rules for networking are divided into 7 different layers, and those layers are known as the OSI model. Now, to give you an analogy, the human body is made up of various systems. The skeletal system, the respiratory system, the nervous system, the cardiovascular system, the muscular system. And if each of those systems are operating as intended, then the goal of the human body is attained, meaning the human lives. Well, networking works the same way. Each of the layers of the OSI model serve a specific function. And if all 7 functions are accomplished, then the goal of networking is attained, which is to say hosts can share data. Now, the goal of this lesson is not simply to memorize the OSI model. The goal of this lesson is to take a look at the purpose of each layer in the OSI model and see how it contributes to the overall goal of networking, which is allowing two hosts to share data with one another. That said, let's just jump right into it, starting with the first layer of the OSI model known as the physical layer. Data on computers exists in the form of bits, that is, ones and zeros. Well, the first thing that needs to exist for these hosts to share data with another is something has to transport those ones and zeros from this computer to the next. That something is the physical layer. The goal of the physical layer is transporting bits. And anything that contributes to moving ones and zeros from this computer to this computer is considered a layer 1 technology. For example, cables all fall under the concept of layer 1 technologies. All of these cables serve the purpose of taking bits from one end and taking them out to the other end. But don't get too caught up on the word physical. The OSI model was written well before the idea of wireless internet communication was ever thought of. Wi-Fi is considered to be a layer 1 technology because Wi-Fi solely exists to carry ones and zeros from one computer to the next. Now, not only do these cables or Wi-Fi exist at layer 1, there are some devices that also exist at layer 1. One of those devices is known as a repeater. In the last lesson, we identified that repeaters simply amplify signals from one end out the other end. In a way, a repeater is really nothing more than something that allows you to extend a wire, meaning it contributes to this goal. Therefore, a repeater is considered to be a layer 1 technology, which means that multi-port repeaters, like hubs, would also be considered layer 1 technologies. All of these items serve the function of transporting bits from one computer to the next. That is the goal of layer 1. Which brings us to layer 2. Layer 2 is going to interact with the physical layer. It's going to actually put bits on the wire and retrieve bits from the wire. Which means whatever this wire actually connects to on this PC is considered a layer 2 item. Meaning the NIC, or the network interface card, that this wire is actually connected to on this computer is considered layer 2. The Wi-Fi access card is also considered layer 2 because it's interacting with those Wi-Fi radio waves. Now, NICs and Wi-Fi access cards don't really look like this anymore, but there was a time when you had to buy separate cards and actually install them into computers and able to access the network or Wi-Fi. Nowadays, Wi-Fi access cards can fit in your smartphone or your watch. The overall goal of layer 2 is what I'm going to call hop-to-hop delivery. Meaning, layer 2 exists to take ones and zeros from this NIC and move it to the other NIC. This is what I'm calling a hop. Now, to accomplish this goal, layer 2 is going to use a specific addressing scheme. That addressing scheme is known as a MAC address. MAC addresses are 48 bits, which are represented as 12 hex digits. Here are 3 examples of a MAC address. Now, in all cases, these are the exact same MAC address. The only thing that's different is how they're displayed. Windows machines typically use the dashes in between the hex digits. Linux machines typically use those colons, and Cisco routers and switches typically use the 4 hex digits with a dot in between. Either way, it's still just 12 hex digits, which are converted into 48 bits. The way it works is every single NIC has a unique MAC address, meaning this computer's NIC over here has the MAC address A1A1, and this computer's NIC has the MAC address E8E8. Now I'm only showing you the first 4 digits of the MAC address simply to conserve screen real estate, but in reality, this is what a MAC address looks like. Either way, this MAC address is what's going to allow data to go from one NIC to the next, i.e. from one hop to the next. So we've identified that NICs exist at layer 2, but there's another type of device that also exists at layer 2, and that is switches. Recall from the last lesson that we discussed that switches are devices which facilitate communication within a network. Meaning, if these two hosts are connected via this switch, the switch is what's going to help traffic move along to accomplish this hop. Moreover, switches allow you to connect many devices to them. If these two hosts want to speak to each other, the switch is going to internally connect these wires such that data can traverse this hop from this NIC to this NIC. So switches are considered layer 2 technologies because they aid in the accomplishment of this goal. Now generally with the internet, you're commuting with things that are far away, not necessarily things that are in the same network. So it's very common for communication between hosts to require multiple hops, meaning we need to jump across multiple routers to get to the target host. Well, each of those routers are connected to a wire using a NIC, and therefore each of those NICs have their own MAC addresses. And layer 2 will handle taking data from the first MAC address and delivering it to the next MAC address. And then from this NIC to the next NIC. And then from this NIC to the next NIC, and then finally from this NIC to the next NIC. So you'll notice in all cases, layer 2 is handling the hop-to-hop delivery of data. Which begs the question, if layer 2 is taking care of every hop, what's taking care of ensuring data goes from this endpoint to the next? Well, that's where layer 3 comes into play. Layer 3's goal is what's called end-to-end delivery. To accomplish its goal, layer 3 is going to use its own addressing scheme known as IP addresses. Now, we unpacked IP addresses in the prior lesson. IP addresses are 32 bits represented as 4 octets, each that can be the numbers 0 through 255. Every host is going to be identified by its IP address. And these IP addresses are what's going to allow data to go from here all the way to here. Now, as you can see from this illustration, aiding in the goal of delivering data from end to end is routers. So routers are considered to exist at layer 3 of the OSI model. Hosts are also considered to exist at layer 3 of the OSI model. But really, anything with an IP address can be considered to exist at layer 3 of the OSI model. Now, at this point, a question typically comes up. And that question is, if we have IP addresses at layer 3, why do we need MAC addresses? Or alternatively, if we have MAC addresses at layer 2, why do we need IP addresses? Answering that question will help reveal how packets flow through the internet. The reason we have 2 different addressing schemes is that each of those addressing schemes serve different purposes. So let me show you. Let's say this host has some data that needs to send to this host. Now, of course, that data is just a bunch of ones and zeros. Layer 2 and layer 3 don't know what that data contains. It's just an arbitrary set of ones and zeros that need to get to this host over here. Since this computer knows the data needs to get to this endpoint over here, it's going to add some layer 3 information to that data. That layer 3 information is going to include the source IP address and the destination IP address in order to get this data from one end to the other. But now this computer knows that the first step will be getting that data to the first router, which will prompt the computer to add layer 2 information to that data, and that layer 2 information is going to have a source MAC address of the computer's NIC and a destination MAC address of the first router's NIC. That's what's going to get this information to the first router. Once it gets there, we can remove that layer 2 information. Remember, the whole purpose of that layer 2 header was simply to get this construct from here to here through the first hop. From this point, this router now knows that this needs to get moved to the next router. And it's going to do this by adding another layer 2 header. But notice this time, the source and destination MAC address identify these 2 MAC addresses. That's what's going to take this packet to the next router. And here, once again, we can get rid of that layer 2 information. Again, the whole purpose of that layer 2 header was simply to get the packet from here to here. Since it did that successfully, we no longer need it. This process will continue with this middle router over here, adding layer 2 information that'll take care of this hop. And finally, the last router in the sequence will add the final layer 2 header, which will take the packet from this NIC to the end host's NIC. Once it gets to the final host, again, the layer 2 header can be removed. The purpose of that header was again just to bring the packet from here to here. Moreover, the layer 3 header can be removed because the purpose of that header was to bring the data from here to here, from end to end. Finally, this gets the data to the computer and the data can be processed by the receiving host. That is why we need both IP addresses and MAC addresses, because they serve different functions. Now, we've been talking about IP addresses and MAC addresses as independent functions, and indeed they are. But I should mention at this point that there is a protocol that's going to tie these together. That protocol is known as the Address Resolution Protocol. It's going to link a layer 3 address, like an IP address, to a layer 2 address, like a MAC address. Now, ARP is crucial to understanding how data flows through a network. We're going to be talking about ARP later on in this module. But if you can't wait, I did write an article series that discusses all the different forms of ARP. You can access that series at pragnet.net/ARP. As for us, that wraps up the first part of our practical discussion of the OSI model. In this video, we discussed layer 1, layer 2, and layer 3, and how each of those layers have a specific goal which contributes to how data flows through a network. In particular, we illustrated how layer 2 and layer 3 work together to move data across the many different hops required to get data from one end to another.
Okay, I'm back. So did people have any questions? I know, Bob, did that clear up how MAC addresses and IP addresses kind of interact? A little better?
Exactly.
Okay, perfect. Anyway, did anyone have any questions? There was quite a bit to unpack in that one.
So they didn't mention what a modem is. Modem converts electrical signals into digital signals. It's a layer 1.
I believe so. I believe so, but I'm not sure.
That's correct.
Okay.
So just to push on that a little bit, the electrical signals on the coax that comes into your house, or fiber cable that comes into your house, is an analog signal, sine wave, and then the modem figures out how to convert that to a digital packet. Is that correct?
It's got to filter it too, because you got you got cable to your TV, comes on the same wire.
No, I understand.
So it's got to get filtered, but extracts it out and it converts it to a digital.
Assuming you don't have multiple things, it's just device A to device B. So the signal goes out and it goes onto the modem. It goes from a digital, so it's like an AD converter, right?
Yeah.
So it goes from DA, from digital to analog.
That's outgoing.
That goes on the wire.
You remember years ago when we used to have to connect our computer up to some other device by taking the telephone and putting it on something?
Yeah, I understand.
And you hear it making all the beautiful tones. Okay,
Right.
That was sending out digital signals at different frequencies.
I mean, keep in mind that everything ultimately is analog, right? They're all analog electrical signals that are being interpreted reliably, hopefully, as ones and zeros, right? So that distinction is somewhat arbitrary, right? It's really not until you're in the software or the computer chips that you're really, dealing with digital, right? The electrical impulses that are going over your coax or going over your twisted pair, or the optical, the light that's flashing inside your fiber optic cable. That's all ultimately analog, and it's just interpreted, right?
That goes back to why you need a repeater, because the analog signal will decay over time.
Yeah,
just because of physics.
That's correct.
And that's what was confusing in my mind, because I wasn't thinking that way. I couldn't understand how a digital signal would decay.
Because you're absolutely right. Because it's ultimately an analog signal that is representing, to another layer in people thinking, that it's ones and zeros, right? And by the way, same thing happens inside a chip. You have transistors that are sending, electrical signals inside a chip. And those decay, those are susceptible to noise, interference, radio interference that can mess with the integrity of that analog signal. So, you all have heard of the, cosmic bit flips, where, all of a sudden you get a little corruption in your memory because some, ray coming from the sun, messes with a zero, something that's supposed to be a zero, and turns it into a one. I'm dead serious. This happens.
Yes.
Very infrequently, thankfully, but it does. Anyway, so I think we can move on unless anyone else has a question.
Roll them.
Okay, I was going to talk about ARP, but I think he's going to handle that. If there are questions, because ARP is an example of how your network learns what's connected to it.
Layer 2 and Layer 3 contribute to the overall goal of networking. We discussed that Layer 1, the physical layer, was responsible for transporting ones and zeros across the wire. We then illustrated how if this host has some data it needs to send to this host, it needs to start by adding a Layer 3 header, which will facilitate carrying the data from one end to the other. Then a new Layer 2 header will be added to carry the data from one hop to the next. This will continue across the entire path between these two hosts. If you haven't watched that video, go ahead and pause this video and watch that one first. There'll be a link in the description. Otherwise, we'll continue right where we left off by discussing Layer 4 of the OSI model, the transport layer. The overall goal of the transport layer of the OSI model is what I'm going to call service-to-service delivery. Let me explain what I mean by that. Here is a computer. This computer has an IP address and has a MAC address. In a pretty common scenario, whoever is using this computer has a web browser open and is browsing the web. But maybe at the same time, that user is also running some sort of chat program, something like Slack or Discord or IRC. And at the very same time, that user might also be running some sort of online game. Well, each of those programs is meant to send and receive data on the wire. All that data will be destined to this layer 3 header to accomplish end-to-end delivery, and this layer 2 header to accomplish hop-to-hop delivery. The question then is, how do we make sure the right program receives the right packets? Well, that's where layer 4 comes into play. Layer 4 is there to distinguish data streams. It's going to take all that incoming data and make sure that the right program receives the right data. Just like layer 3 had an addressing scheme to do end-to-end delivery, and layer 2 had an addressing scheme to do hop-to-hop delivery, layer 4 is also going to be using its own addressing scheme to accomplish its goal of service-to-service delivery. Layer 4's addressing scheme involves ports. Now there are two sets of ports. There's 0 to 65,000 for TCP and 0 to 65,000 for UDP. TCP and UDP are two different strategies for distinguishing data streams. TCP favors reliability and UDP favors efficiency. Both TCP and UDP are simply different strategies for accomplishing the goal of layer 4. Their inner workings are both significant and fascinating, but unfortunately they are outside the scope of this lesson. They will both be covered in detail in a later lesson in this course. But the way they work is that every single program that's expected to receive or send data on the wire is going to be associated with a particular port number. Then, when data arrives on the wire, it's going to include a layer 4 header in addition to the layer 3 and the layer 2 header that we've already discussed. That layer 4 header will indicate which particular program should be receiving that data, and that's what layer 4 is going to use to make sure the right program receives the right ones and zeros. So that's a high-level overview of how layer 4 distinguishes data streams. But let's pick it apart in more detail. Here is a client and 3 servers. As we discussed in the first lesson, a server is nothing more than a computer which is running software which knows how to respond to specific requests. Each of these pieces of software is assigned a predefined, well-known port number which correlate to the underlying network application. Let's say Bank.com is listening for secure web request using HTTPS, which is assigned TCP port 443. And the server for Site.com is responding to general web request using HTTP, which by default listens on TCP port 80. And this chat server is running IRC, which stands for Internet Relay Chat, which is an online chat application which runs on UDP port 6667. When the client is making a request to these servers, it's not only making a request to the IP address, it's also going to make a request to the specific port in question. Then, for each request made by the client is going to choose a random port number to use as the source port for the connection. So a connection from our client to Site.com would look like this. It includes a source port of 9999. That's the port that the client randomly selected for this particular connection. The destination of this packet is destined to the IP address of Site.com, going to TCP port 80, which is the HTTP application. Keep in mind that the source and destination IP addresses are going to exist in the layer 3 header of the packet, and the source and destination port are going to exist in the layer 4 header of the packet. Now, this randomly selected source port is actually very important. It is actually the port the client will listen to for the response to the original request. Meaning, when this server responds to this web request, that packet will look like this. Notice the destination port is 9999. That's the same port that was initially selected by the client randomly on the outbound initial packet. So for all connections, there is always a source port and a destination port that are involved. The destination port is typically governed by the application in use, and the source port is randomly selected by the client. So our connection from the client to Site.com has the following attributes. It is a TCP connection from this IP address and port to this IP address and port. Notice that in the initial packet, this was the source and this was the destination, and in the response packet, it's the exact opposite. This was the source and this was the destination. Now this process occurs for each connection made by the client. In each case, the client is selecting a new random source port. This makes it so that when all these servers respond, whatever comes back on port 8888 will be given to the web browser, and whatever comes back on port 7777 will be given to the IRC client. In this way, the data streams are kept isolated from each other. These ports will ensure that the right application gets the right data. This process also allows the client to make multiple connections to the same server. Consider when you are browsing the internet. I imagine you've often had multiple tabs open to the same website. Well, the reason each of those browser tabs don't accidentally display the data from another tab is that each time you open a new tab, your client, meaning your web browser, generates a new random source port. So that is how data streams are distinguished from one another. It is a function of UDP or TCP, which are both layer 4 protocols, and again, layer 4's ultimate goal is what I'm calling service-to-service delivery of data.
So one quick thing. He mentions TCP and UDP, which are by far the most common protocols used in IP for communicating data. But there's another one that you often use, which doesn't use ports like this. It's called ICMP. And if you ever use the ping command, that's what it's actually doing. So ping does not use TCP or UDP. It sends it's a control message that is at a super low level that just really allows you to check whether a host is alive and responding and able to be connected. So if you ever see ICMP, understand that that's also sitting, I believe, in this layer 4 level. And it doesn't use the standard IP address port addressing scheme that TCP and UDP use. Anyway, figured that might be useful.
Which finally brings us to the last 3 layers of the OSI model. Back when they first created the OSI model, each of these layers had a distinct function independent from the rest. However, currently, the distinction between these layers is somewhat vague. Every application is in fact free to implement the functions of layer 5, 6, and 7 as they choose. Therefore, often, these 3 layers are simply considered as a single universal application layer. In fact, the other popular internet communication model actually does exactly that. The TCP/IP model combines all the functions of the OSI layers 5, 6, and 7 into a single layer. Now, the goal of this module is to teach you how data flows through the internet, and the most critical layers to understand for that is layers 1 through 4. Therefore, we aren't going to pick apart the original intended distinction between layers 5, 6, and 7. If you're curious, however, go ahead and let me know in the comments below, and I can cover it in another video. As for us, we're going to follow the TCP/IP model's lead and simply consider all 3 of these layers as the application. So now that we've talked through the entire OSI model, I want to show you what's actually happening when hosts are communicating to each other using this networking stack. This host has an application that's going to generate data that is meant to be sent to the other side. What that host is going to go through is what's known as the encapsulation process. That data will be first sent to layer 4. Layer 4 is going to add a header to that data, which is going to facilitate the goal of layer 4, which is service-to-service delivery. In this case, it is a TCP header, which is going to include the source port and destination port for this particular data. The construct of a layer 4 header plus data is known as a segment. That segment is going to be passed down the OSI stack to the next layer, in this case layer 3, the network layer. And the network layer is going to add another header to this data. This header is going to facilitate the goal of layer 3, which is end-to-end delivery, meaning in this header you'll have something like a source IP address and a destination IP address. The construct of a layer 3 header and its data is known as a packet. Now notice that inside the data of the packet is the layer 4 header that was above it. But from layer 3's perspective, it doesn't know or doesn't care what's inside that data. It's simply a bunch of 1s and 0s that need to be delivered to the other end. Either way, layer 3 will then take that packet and hand it off to layer 2. And layer 2 will once again add another header to that data to accomplish layer 2's goal of hop-to-hop delivery. Meaning, this header will include something like a source MAC address and a destination MAC address. The construct of a layer 2 header and its ensuing data is known as a frame. and that frame gets converted into ones and zeros and finally put on the wire. On the other side, the receiving host is going to do the opposite process. It's going to do de-encapsulation, meaning it's going to take those ones and zeros off the wire to convert them back into their frame. Layer 2 is going to look at the layer 2 header to make sure that it is indeed addressed to this host's NIC. If it is, it's going to discard that header and pass that up the stack. Then layer 3 is going to look at the IP header to confirm it is indeed addressed to this host's IP address. If it is, it's going to discard that layer 3 header and pass it up the stack to the transport layer. Layer 4 will then take a look at the layer 4 header to identify the port that this data is destined to, and will deliver the data to the appropriate application. And the application can then finally process the data. That is the process of encapsulation and de-encapsulation. Notice each layer is going to add information to the data in order to accomplish its goal. And this brings us to the final idea I want to communicate to you about the OSI model. Throughout this lesson, we've mentioned that networking devices operate at specific layers. For example, switches and routers operate at layer 2 and layer 3 respectively. What that means is that they only look into the datagram up to their respective layer. For example, switches, which are layer 2 devices, are only looking at the frame, meaning they're only looking at the layer 2 header to make a decision. They're not looking inside the data payload into the layer 3 and layer 4 headers, which we know exist there. They're only looking up to the layer 2 header. Moreover, we've discussed that there are various protocols which operate at specific layers. For instance, the IP protocol is a layer 3 protocol. TCP and UDP are layer 4 protocols. That said, neither of these are strict rules. There are exceptions to each of these that exists. For example, if you take a router which typically operates at layer 3, but configure access lists on that router, now that router is looking into the layer 4 header to make a decision. So the router isn't purely a layer 3 device anymore. Moreover, earlier in this lesson we discussed the ARP protocol, and we discussed how ARP links a layer 2 address to a layer 3 address, links an IP address to a MAC address, which means ARP doesn't purely fit in layer 3, nor does it purely fit in layer 2. The point I'm trying to make is that the OSI model is simply a model. It's not rigid rules that everything in networking adheres to. It's simply a way to conceptualize what is required for data to flow through the internet. And that wraps up our lesson on the OSI model. The main takeaway for this lesson is understanding that each layer of the OSI model has a specific function that contributes to the overall goal of allowing two hosts to share data with one another. Each layer uses its own addressing scheme to accomplish their various goals. And finally, there are various devices and protocols which operate at specific layers of the host does.
All right. So we got through all of the networking fundamentals that you might ever want to know. So hopefully that was useful. In this next video, I apologize. I think it's a very good talk, but he does repeat himself a fair amount on certain topics. So forgive him. Anyway, did anyone have any questions about that last talk? Yeah, Larry.
Basically, simplistically, if I want to send an email to somebody,
Yep.
okay, I put in the email address. What happens to that afterwards so
Sure.
it gets to somebody?
Sure. So that is happening at the application layer at the top. So what's happening is that email is getting converted into something that's called an SMTP. It's the Simple Mail Transport Protocol, which is a layer, whatever, 7, it's up at the top above what he discussed. And that includes headers like the source email address, the destination email address, and there's encapsulation of the mail body inside of that too. And then your computer, the client, okay, will talk SMTP to a mail server. And there's a sequence of messages. It turns out there's a message that says, hello, okay, and then then the mail server will say, how are you doing, or go away. This next one will be, I want to send mail to this person, okay, and you talk about, and I'm sending it from this person, and here's the body. So that's kind of basically what it is. It's a very straightforward protocol that takes place. And then So to get that hello message, you're now getting into, TCP IP, or the TCP layer with ports and IP addresses. So that's how the raw data is getting sent across. But SMTP is the protocol that is how mail is communicated. And then there's a sequence of routers and relays, that are used to send mail, hop to hop through a variety of different places.
How does it know the address of the individual? Where is that information contained?
So the way this works, are you guys familiar with DNS? The DNS is how you map a name like google.com, okay, to a set of IP addresses. So, for example, let's suppose you want to send a mail to someone whose address is joe@google.com. So, what you would do, your computer would first go to the DNS server for google.com and say, what are the IP addresses of the mail servers that are responsible for receiving mail to people whose email address is at google.com. And it'll give you a list of names, server names. Those are called MX records, mail exchange records. And then your client will pick one of them and send mail to that server using SMTP. And it's up to that server to say, oh, this is intended for Joe at google.com, so I will deliver it into Joe's email address. And in fact, there's even redundancy built in. You could have multiple MX records. So if mail server 1 is unavailable, then you can go and try mail server 2, etc. So that's all part of SMTP. Does that make sense?
Thank you.
All right. In the interest of time, yeah.
A quick question.
Yeah.
If it's too much for this, just tell me. When we're sending packets of data between two places, sometimes those packets are large, and I'm not going to define large, but they're more than what a packet size should be.
Yes.
And there are other issues concerning multiple segments. I don't know what the right term is. Multiple chunks of the packet.
Yeah.
Didn't talk about packet sequencing or retransmission and all that.
That's a much more complicated topic. So, and that's kind of goes into the basis of TCP versus UDP, for example. TCP is a stream protocol. So what it does is it takes just a sequence of bits and breaks it up and has all kinds of stuff to make sure that if the packet gets dropped along the way, okay, it can be retransmitted and reassembled into the correct order. That's all handled at the TCP layer.
Seth, instead of getting into the weeds, when you said TCP, that's good enough. So the TCP layer handles all that stuff to make sure to ensure the integrity of the packet of the data.
Yes, but if you want efficiency and you choose to use UDP, then you got to do that yourself.
Okay, understood.
All right.
TCP, thank you.
Yes, that's why most things are written in TCP or use TCP because it's easier for the application person and it works really well. All right, this is the section on VLANs.
Today in Dave's Garage, we're talking about VLANs and why you should likely have one. So what is a VLAN and why do you care? Well, it all depends on what you have running on your network, like if you have any Internet of Things devices on your home network. For example, if you have any cameras, doorbells, light bulbs, thermostats, or refrigerators on your home Wi-Fi, then you definitely need to know about VLANs. VLAN stands for Virtual Local Area Network, and it is a concept used in computer networking that allows for the creation of virtual networks within your physical networks. Imagine your house was wired with two completely different networks and that it used colored cables, red or blue, each on its own, and the switches never connected each other. A VLAN is a little bit like that. In the case of a virtual LAN, however, they share the same cabling while actually being different networks. It enables network administrators to partition a single physical network into multiple distinct logical networks. Now, each VLAN functions as a separate network with its own resources and traffic, but they all share the same physical infrastructure, i.e. the cabling and the switches. Perhaps it's best to think about it as pipes within pipes. Imagine your LAN is the big white outer pipe. And within your big white LAN pipe are some smaller pipes in red, blue, and green that run inside your outer pipe. The packets on each network can't leave their small pipes, so the small colored pipes within are like a network within a network. Let's call the red pipe the red VLAN. Anyone connected to the red VLAN can see all traffic for everyone else on the red VLAN, but they can't see traffic on other devices or the other colored pipes, and depending on how the rules are set up, even within the big white pipe itself. And similarly, we have a blue pipe for a blue VLAN and a green VLAN as well. And because the clients connected to the red VLAN can't see into the other colored pipes, our network is now effectively partitioned into the main LAN plus 3 new VLANs. They all connect back to the router, which is where they were created, and each has access to the internet through that connection. Let's call the big white pipe our LAN, which is where our general untagged home traffic goes, and then each isolated VLAN will have a tag, or an ID, associated with it, like red, green, or blue. Let's make the red one the danger zone. That's where we'll put all of our cameras from offshore vendors, doorbells that record to the cloud, and dishwashers that inexplicably need to access a central web server in order to clean your plates. But these devices have no reason and indeed usually no business even looking at our Windows PCs or MacBooks. They need connectivity to the internet and to the cloud, but not to our other home LAN clients around our house. Perhaps we make the green zone a VLAN that's safe for kids with different content, time, and bandwidth restrictions. By dividing a large network into smaller, isolated segments, VLANs reduce the amount of broadcast traffic, which can significantly improve network performance. This isolation also enhances network security, as it limits the spread of broadcast storms and contains network problems within a single VLAN, preventing them from affecting the performance of the entire network. A broadcast on the blue VLAN only reaches the blue clients, and it doesn't bother the rest of the network. Another important purpose of VLANs is network segmentation. This feature allows for better control over traffic, as administrators can group together users' devices with similar needs or roles. For example, a company might have separate VLANs for its accounting department, its HR department, and guest Wi-Fi, ensuring that sensitive data is only accessible to authorized users. This segmentation also simplifies network management and troubleshooting, as problems can be isolated and resolved within a specific VLAN. How do VLANs work? Well, VLANs operate way down at the data link layer, which is layer 2 of the OSI network model. They work by stamping or tagging network frames with a VLAN identifier or ID as they pass through a network switch or router. Earlier, we used the colors red, green, and blue, but it's normally just an integer ID, so 1, 2, and 3. This ID designates the frame to be a specific VLAN. When a device sends out a data frame, the network switch adds the VLAN ID to that frame, and when it receives the frame, it reads the VLAN ID and forwards it to the appropriate VLAN. This tagging process ensures that data is only shared between devices on the same VLAN, even though they might be physically connected to the same switch. It's like having multiple separate networks running on the same physical infrastructure. The switch uses these tags to segregate and manage traffic, ensuring that data intended for one VLAN never ends up on another. This separation is crucial for maintaining the security and efficiency of the network. To put it more simply, if two frames come into a switch and have different VLAN tags, it's like those frames are on completely different disconnected networks. One of the major benefits of VLANs is enhanced network security. By segregating different parts of a network, VLANs can limit access to sensitive information, reducing the risk of data breaches. For example, a VLAN in your home business can be set up to restrict access to only those authorized to view sensitive financial or customer information. This isolation also helps in containing network problems. If a security breach or network issue occurs, it is again confined to that particular VLAN and doesn't affect the entire network. We achieved this level of isolation in our earlier example by placing all of our IoT traffic into the red zone. And we could anoint the blue zone as the business zone and the green zone as the kids network, whatever makes the most sense to you. VLANs also contribute to improved network performance by, as we said earlier, preventing broadcast storms from propagating across VLANs. Additionally, VLANs provide better network management and flexibility. Network administrators can easily add or modify VLANs without changing any cabling or anything about the physical setup, allowing for quick adjustments to network structures as organizational needs change. In reality, this isn't likely to be a major factor within a home or a small lab, but it can be a big deal on larger corporate networks. VLAN tagging is a crucial concept in the operation of VLANs, and it's defined by the 802.1q standard.
Just in case, I figured I better clarify. A nice way to think of VLANs is when you think about the previous videos, you have a switch. So all of the computers that are connected to that switch are on the same network. Okay, that's kind of what defines the network. And in order to have multiple networks, you would need multiple physical switches. So what VLANs do is allow you to make your one physical switch appear as though it's three or it's multiple virtual switches. So does that make sense? So it's really, you can do the same thing without VLANs. You would just need lots of switches. So that's really, if hopefully that clarifies what VLANs are. It's really a way of saving hardware.